Right, I'm going to run through this design for this thing. I haven't drawn a schematic for it yet. I've got a rough idea in my head what I'm doing, but I figured, well, let's go through this, and if it works, you can see why it works, and if it doesn't work, you can go back to this video and you can say nah. However, what we need at the very beginning of this whole radio is we're going to have a aerial input. That's going to go to our coupling coil on our first aerial coil, which is tuned to the signal. That in turn is a resonant coil, as we've already discussed, which goes to a tuning capacitor. And then bloody pen's running out. God, look at me. Nothing goes right, does it? Nothing goes right. And there's another pen that's worn out. What else have we got in here? Here we go. We'll have a colour change. Okay. So, from our first tune circuit, we go into a... Can you see that? Is it visible? Probably not. We go into the control grid of a pentode. The reason we're using a pentode as the RF amplifier is simply because it has something called a screen grid, which shields the anode inside the envelope, the valve envelope, from the control grid and the cathode. This allows us to get extremely high gain at one stage without the thing be oscillating, having feedback problems and becoming unstable. Now, in order to bias up a valve, all electronic devices without exception require what they call biasing. It means setting the DC conditions so it operates in the linear mode which you want it to operate in. So with valves we use what's called self-biasing, automatic biasing. We basically lift the cathode above ground with a resistor, and this in effect makes the cathode slightly positive as reference to ground. The valve actually sees it in a slightly different way. It sees its grid as negative compared to the cathode, so consequently the valve has turned itself off. Now it gives it an automatic bias, because if the valve tries to turn itself on more, the cathode will increase in voltage, which it makes the grid more negative, which tends to turn the valve off again. So that's quite a neat and fancy way of doing it. Now the cathode resistor is not normally that critical, but you've got to get it, reasonably close. The testament to valve radios is the fact that, that some of them, 80, 90 years old, and some of them are still going. There's an awful lot of valve radios still left in the world that actually go. So, what with grotty components back then, resistors I think had probably about a 20% tolerance one way or the other, and they certainly drifted in, over the last 70, 80 years, and these things still perform. There's nothing critical really with normal valve technology. It was very forgiving. But however, I digress as usual. Now our anode circuit, this is the amplified RF, now appears at the coupling coil of our second RF's tuning stage, which is another tuned circuit. Now because the frequency we're operating at, which is AM broadcast band, that goes from about 550 up to 1700, the selectivity of these will vary, something shocking. They're never going to be more than maybe 100 kilohertz wide, simply because the loading effects and the frequency tuned circuits are, even if they've got a fairly high, shall we say, Q, they still don't have a nice shape factor. The shape factor of a normal tuned circuit is shaped like that. Crystal filters will be shaped more like this. That's why we spend big money in crystal filters. So, if it's receiving a signal there, that's fine. But as that's not the only signal in the spectrum. Might be a signal down here. Depending on if it was a crystal filter, that signal would not even appear in the radio because it's way down in the 0 point, if you take that as 0 and that is 10, for instance, you know, that's a 0. But on this selectivity curve of these RF coils, you know, it's probably still a 5. So it's quite possible that that's going to get, well, it is possible that's going to get through. And this is what concerns me with this idea of these synchrodynes, is just what effect is it going to have. I honestly think it's going to cause a whole lot of heterodynes and whistles, but we will see, we will see. Now another good thing with pentodes is that they've got an incredible amount of gain. If we work on the fact that we're going to have about, I don't know, we don't need a lot of sensitivity on the medium wave band, it's such a noisy band. So, you know, so we're looking at 10, even 20 microvolts is more than adequate. So if we go for a maximum sensitivity, or a nominal sensitivity of 20 microvolts, a good pentode RF stage, especially down at this frequency, probably give a gain of, easily times 20. So it's going to give us, what, 20 times 20 is 400 microvolts here. 400 microvolts, give or take. It's not only the gain of the valve either, we've got the voltage amplification of these coils, which are basically a transformer. They work the same, pretty much. If you've got, say, 10 turns on the primary and 100 turns on the secondary, theoretically you're going to have 10 times the voltage on the secondary that you have on the primary. And they are voltage amplifiers. All of these high impedance RF circuits do depend on voltage, not current. Ideally there'd be no current flowing in and out of a grid of a valve, but unfortunately there is. You can't do anything about that. Now with a screen grid, as I think I've said, it separates the, it stops the anode basically from seeing the cathode or the control grid. There's a thing in valves called a millicapacitance. It's a pain in the arse thing, but you can't get around it. The screen grid in a pentode actually shields and diminishes that capacitance to a level where you really don't have to take it into consideration, especially at these frequencies. So what we do with the screen grid, we bypass it with a capacitor. So any RF is bypassed straight to ground, and we give it a positive voltage. So that's going to be HT plus. The reason for this is that the electrons are expelled from the cathode and attracted toward the anode because of the positive voltage. The screen grid having a positive voltage on it also speeds the electrons up on their way toward the anode. So the gain of a pentode can be controlled quite good with the actual voltage you put on the screen grid. So okay, now we're going to go from the second tuned circuit straight into a mixer. Now here we're going to use I've decided to use a thing called a heptode. A heptode is a valve with 5 grids. 1, 2, 3, 4, 5, and a cathode. This particular valve, the ECH84, which I'm using, I don't know what the American equivalent of that is. Americans never really got into heptodes stuff for mixing. Mainly Europeans did this. These are amazing valves, you know, amazing performance. However, what we're going to do is bias this one up. Now, just before we go any further, the ECH81, ECH84 series have also got a triode in the same envelope, valve envelope, and their cathodes, because there's a limitation in pins, these valves have 9 pins, an oval base. The two cathodes, the cathode from the heptode and the cathode from the triode, are actually common and come out on the one pin. So to save a bit of grief, so you can use both valves for totally different purposes, it's best just to ground the cathode. And the only way you can bias it at that point is by having what's called a grid leak resistor. And generally they're 1 meg ohm. Seems to be about the nominal value. It's low enough not to cause the valve to cut off completely, but it's high enough not to load the tuned circuit to any great degree. So to prevent shorting out that DC bias, we have a coupling capacitor. That can be something small like 100 picofarad at these frequencies. Not critical. That's a tuning cap, that's a tuning cap, and these are joined basically on the same shaft, ganged together. Now, the idea of the heptode is we've got two screen grids. We've got the second grid in as a screen grid, and the fourth grid in is a screen grid. Now these are designed to separate the oscillator injection grid, which is grid number 3. The screen grid separates that in a capacitive way from the control grid, and it also, the second screen grid prevents the anode seeing either the oscillator injection grid or the control grid from seeing the anode. Oh God. So that is the case of the pentode. We just RF bypass the screen grids, and they are also taken to a positive voltage. We'll get back to that later. Now, the output of this mixer is going to be an audio frequency. This is the audio from the signal that we're receiving. So the first thing we need to do is shunt any RF energy that appears at the anode to ground. So we'll have a capacitor there, and it only has to have a low impedance to RF, so we'll say, you know, that should have a roll off of, start rolling off at about, I don't know, 1 or 2 kilohertz. We'll see how we go with that. It's all subjective. Now we're going to need, before we go any further, I'll make a list of the valves we're going to use. I've got a ton of ECF80s here. I don't know what the American equivalent of these is. 6BL8 maybe, I'm not sure. These are a triode and a pentode in the same envelope. As I've said, the ECH81, 84 are similar valves, but they do exhibit very different properties, as I found out. That's a heptode, or a hexode, I don't know what the difference is. Heptode or hexode, and a triode in the same envelope. And so we're using 2 ECF80s and 1 ECH84. That gives us 3 triodes, 2 pentodes, and 1 hexode, heptode, whatever, call it what you like. So we've actually got 3, 4, 5, 6 valves. So even though we've only got 3 valves, it's actually going to be a 6 valve set. So we should be able to make this thing perform quite well, I reckon, given what we've got. So, and there's other problems with this too we've got to be very careful with, but we'll get to that later. So up to this point we've got an amplifier amplifying the signal frequency, we've got a mixer, and we're getting it back down to audio. So let's do the easy bit first. We've used up 1 pentode. We'll need another pentode. Now, for reasons I'll go into later, I'm going to use a pentode for the oscillator, local oscillator. Now this again is biased pretty much the same way. We use cathode biasing, and we need a oscillator coil with a feedback winding. So there's our main oscillator coil, a resonant coil, and that capacitor is again gained. So these 3 capacitors are all tuned together, as we have here. All 3 capacitors are tuned together. Now, to make this valve oscillate, we have to couple the top of the tune circuit into the control grid. And the control grid, because we are capacitive coupling this thing, for reasons I'll go into later, we need a grid leak. Now to stop this thing, what they call squedging, oscillators don't normally have any sort of a negative feedback circuit, so if they get too much feedback they start doing weird things. So to prevent that happening, we got to lower the Q of this quite considerably. We don't want any more gain in this than what's necessary for the thing to just keep itself alive. So we're going to use something like a 47k. It's a fairly low value for a grid leak. And again, we can use, I don't know, 100 picks in there because of the frequencies. We don't want that to attenuate the signals frequencies that we're using. So 100 picks is probably about right. Again, we can have a bit of self-biasing. You can look at the valve specs for different curves. But you know, we'll probably get away with, I don't know, 470 ohms here. It'll probably be fine. RF bypass at 0.01. These are just round figures because valves are really not critical. You know, you can go along after you built this thing and tweak it. You know, occasionally you find somewhere where you've gone a bit awry. But generally you won't be able to tweak it much. They're fairly tolerant, very tolerant. The same goes for this one. You know, we don't want this to draw too much current, so we might make that 1k. Better to be too high than too low. And again, we use a 0.1 bypass on the RF amplifier cathode. And we feed the anode of the, this is called an Armstrong oscillator. We feed the anode of the valve back into the coil in the correct sense to make this oscillate. And that will go off to the HT. It's generally good practice to put a resistor in here and a bypass capacitor. There's quite a lot of RF activity on these coils, and you know, you're probably going to get about, I don't know, depending on the HT voltage, you're probably going to get about 20-30 volts of oscillator voltage. You don't want that floating around everywhere, so you know, we use a bit of power supply hygiene. Now the where's that one? The third grid on the mixer tube, the grid, you know, you're looking at probably, I don't know, 470k at these frequencies is pretty high, and we'll also need a grid leak on that one as well, so we'll make that the standard 1 megohm as well. It's not particularly critical. Now, I have never used a ECH84 to direct convert an RF signal down to an audio signal. I don't know what value to make this here, but I do know that pentodes, and this is just like a double pentode basically, pentodes have an extremely high anode resistance. So we're going to make that fairly high. I'm going to make that 120k. And we'll see how we go with that. Whatever you make that figure, that will work, but how well, I don't know just yet. The screen voltage, well, screen voltages aren't all that critical, so we could perhaps, I don't know, join these two screens together. Let's do that. We'll join those two screens together, and we'll take that to that's HT there, HT plus. We'll put a resistor in here, and we'll just make sure we bypass that. Might save a few components. In fact, we could probably get rid of that resistor and that capacitor as well. We'll see how we go. Now, we've got everything we need to have a working radio, except we need an audio stage dummy. So now we've used up 2 pentodes and a heptode. So we've used up our 2 pentodes and we've used up our heptode. We've got 3 triodes left. So let's use a triode as an output audio amplifier. Again, it's a standard circuit arrangement where we have the cathode biasing, we have a grid leak, and we have a output transformer here as an anode load, and this of course drives our speaker. So what we also need in this radio is a volume control. So we'll put a volume control right there. The reason for a coupling cap, a lot of circuits you see don't have grid leak. Here they use the actual volume control as a grid leak and do away with this resistor and that capacitor, but it sometimes leads to a voltage running through the volume control internal wiper, and it causes it to crackle when you move it. It drives you nuts, so I tend to just put those extra two components in. We'll have another triode here as a audio preamp. Again, it's just a duplication really of that stage, and we'll take the anode down to the wiper of the volume controller through a coupling cap. Because our frequencies are now very low, we need to use larger capacitors. The standard capacitor for audio circuits with valves is a 0.1. It was always what we did in the industry. If you're in doubt, stick in a 0.1. So because we're dealing with high impedance anodes, triodes aren't quite as high as a pentode, but it's still pretty high. We use a high value volume pot. The standard value for valves used to be about 1 meg, 500k to 1 meg. These days these values are getting pretty thin on the ground. I think about the maximum you can find now, I think, is about 100k, so we probably won't have much option but to put in a 100k volume pot. Now, because this valve is drawing quite a bit of current, because it's an audio output stage, we want this fairly low to stop it going into clipping. So, depending on which triode we use, I think the triodes in an ECF80 are good for, I think they're good for a couple of watts. So we want that fairly low, so I'm going to guess 220 ohms for there, bias it on fairly hard. Because that's a very low impedance point in the circuit, this here we're going to have 47 microfarad. We'll probably do that. That will bypass all the low audio frequencies. This here again, because we've got 100k here, we could probably put 100k in here as well. We don't want, because the valve's passing a lot of current, we don't want to have too much negative voltage appearing on the grid, especially as we've got cathode biasing as well. This one here, we don't want this drawing too much current, so we're going to use 1k, and again we can use a 0.1 on there, because this valve's actually just coasting along. We can make that probably, I don't know, 100k. Let's keep everything quite simple, and they can be joined together to the HT voltage, HT plus. Again, our grid, we'll use that grid leak, and again a 0.1 coupling cap, and that will connect up to there, that point there, and we could probably get away with 1 meg there as well. So that's our audio stage, our oscillator, and now we've used up 2 triodes, so we've got 1 triode left. What do we want that to do with that? Well, we're going to make some way of synchronizing this oscillator to the input signal. So let's draw our triode. I have this idea here. So just in passing, we've got to be careful because we're using 2 devices in one envelope, i.e. a triode and a pentode, we've got to be a bit careful here. Like, we can't use, for instance, the triode in the hectode. We can't use it, say, as the audio output triode, because it's just a it's a pissy triode basically. It's a very low power triode, almost like an afterthought that they put into the hectode. So we can't use it for any great power. So we really need it for something that's just sort of coasting along. And so we're going to use that, I'm going to call that V1A. This is V2A. This is going to be V3A. We can use the triode in this here because what I'm trying to get at is when you've got two devices in one envelope, they're physically close together, so you've got to be careful of feedback problems. Because that's operating at RF and this is operating at AF, we can use that triode and we can call that V1B. This one here we can use out of this one. That's the pentode of V3A, so we'll call that V3B. There's going to be no, because that's an RF oscillator and this is an audio stage, it's not going to interact because of the physical closeness. In fact, we'll make that different. Because this valve's going to run, this triode being the output valve is going to run quite hot, we don't want it actually near an oscillator. So we'll make that one V1A. So this valve is basically just coasting along. It's not going to get nearly as warm as that one. So we'll use the triode and not that pentode envelope. Yes, that's better. And we'll use that one and that triode to V1. So we want V1A. I'm getting cocked up here. V1B. The triode out of that one there is V3B. V3B. And that leaves us with a triode out of the heptode, which is here. We're getting there now. So that's V2B. V2B. Now we're going to design this. So again, we can have a 1 meg grid leak. We can have a small coupling cap of 100 picofarad. So we're dealing with RF. What we're going to do, we're going to steal a bit of the RF that's coming in from the signal amplifiers, and we're going to isolate it through this triode. Now, I've got a feeling, if we actually get rid of that capacitor there, if we upset the bias slightly by varying the screen grid voltage on the oscillator via this valve, in fact we probably don't even, no, we don't have to do that because that's automatically grounded. That cathode's automatically grounded with that one. Got to remember that. So here we have, this valve will see a waveform such as that. So that valve also has a waveform because it's the oscillator. So by varying the gain, this is what I'm getting at, by varying the gain on the screen grid of this oscillator valve, we should be able to pull the frequency. It only has to be a few hundred cycles, any more than that we don't want. The whole idea of it, when we tune into a signal, then that valve there will pull the oscillator into synchronism with the signal that's going into the mixer. That's the theory, and that is probably what I'll make, and then I'll tweak it once it's running. So just to double check, we've got 2 pentodes, we've got 1, 2, 3 triodes and a heptode. So yes, it's all looking quite good. It's all looking quite good. Let's get that built now and we'll see if it works.